Okay, so this is a bit more subtle, but not necessarily impossible. Again, we need to know a couple of things first of all. One of the things about tree is if it just has a root node, then we often consider that the height is 0, okay? The height at the first rank is going to be 1, the height at the second rank is going to be 2, okay? So we already know the answer to our problem. The height of this particular tree is 2, okay, great. But again, if we're writing a recursive algorithm, we need to think about the base case and the recursive case. With this algorithm, to find the height, what is the base case going to be? Well, you've kind of answered it already because you've said once you have no more children to recurse to, then that is the base case. Okay, and that's true here. Okay, the base case is you've got to a leaf. Okay, the recursive case is there are still children to visit. Okay, so these are kind of some of the nice repetitive things about writing tree algorithms is you kind of already know what your base and recursive cases are going to be. But to sketch out this, okay, height of this tree starting from the root, let's start with the base case. If that particular node is a leaf, it has no children, then, well, if we imagine this only had a root node, we'd have to return the answer of 0. Okay, so if we've got to a leaf node, counterintuitively, think about just a root node where the answer is 0, it makes perfect sense. If you're at a leaf and the root is the leaf node, it has no children, we have to give an answer of 0, so this gives us 0. Okay. Otherwise, we need to then determine, okay, well, if we're returning 0 here, we want to be able to count the levels. So what are we actually trying to do? We're trying to find the height of the tree. I know maybe it's a bit subtle, but what we're actually trying to find is which subtree goes down the furthest. Okay, so this subtree goes down 1 level. This particular subtree here, the right one, goes down 2 levels. Okay, so we'd ideally like to say the maximum height isn't 1, but it's actually 2. So what we want to basically say is, well, what is the maximum left height and compared to the right height? Okay, so if we can work out the height here and the height here, we just want to know which is the biggest. Okay, and that kind of helps us. So if we say, okay, we can calculate the height for the left height, that will basically be keep recursively calling height on the left child. Okay, so just keep going down here. Okay, and we can also do the same for the right. We're still not completely there yet because what we're missing is something counting. Okay, so we want to basically find out what is the maximum of these two numbers. Okay, so we basically want to ask which is maximum. The thing that we're missing here is every time we go down a level, we want to remember that we went down a level. So we can add 1 onto this to act as a counter. Okay, and I think I forgot my return there. Otherwise, that's not a proper call. Okay, so again, if we go through this, if I take the maximum of B and, or else, let's do that differently. Okay, let's take the first call, which is we want to find out the height of this tree starting at A. What that really means is we want the maximum of a recursive call, the height of B, height of C, and the maximum of those plus 1. Okay. B isn't a leaf node, so we also need to know the maximum of the height of D and the height of E, also plus 1. Oops, not plus 11. Okay, C is already a leaf node, so there's no more recursion there. Okay, now we're at the leaf nodes. This returns 0, this returns 0, but crucially we add 1. Okay, so then if I put this in yellow again, 0, 0, we're adding 1. So this returns back 1 here. This is a leaf node, so it's 0. So the maximum of 1 and 0 is 1, plus another 1 returns us an answer of 2 back up here, which gets us the answer. Okay, again, incredibly subtle, but it is a nice way to kind of solve this problem.